Hey there, welcome to my channel. Today is the day where we'll start training our first machine learning model. So as you can see, we are starting from scratch. We just have a main method. I've only imported 3 libraries which we'll use. We will use NumPy for the computations, Plotly for the plotting, and TQDM for getting nicer progress bars in our terminal. But essentially you can leave TQDM out. It's just for aesthetics. Okay, so let's start coding. So first of all, I will define a seed, such that we can make sure that we obtain the same result each time we execute the script. So then we will load the dataset, or let me specify it more precisely, generate our dataset. So a dataset is the following. So we have only one feature, which is x. X will be equal to 100 times nprandom.rand 1000. So we want to generate 1000 data points. So that is why 1000 goes in here. And what does nprandom.rand do? So basically we are sampling 1000 data points from a uniform distribution in the interval from 0 to 1, where 1 is not contained in the interval. Okay, and then we can define our target label, which is 0.5 times x plus 5 times nprandom.rand 1030. So we can also define the number of instances, which is 1000 in our case. So we can substitute it in. And for y, we are using nprandom.randn. And randn, with that method, we are basically sampling from a Gaussian distribution. And whenever you want to sample noise, the Gaussian distribution is a good choice. And as you can see, this is a linear model. We have the linear part, which is 0.5 times our feature, plus some noise, plus 30, which is the bias term. And basically what we want from our machine learning model is to be able to describe these y values, to be able to fit these data points, these generated data points. So let us have a look at the shape of x and y, if that is correct. So when we execute our script, what we get is that we have an array with 1000 entries, which is correct. Okay, so far so good. Let us continue by initializing the weights and constructing a model. So what kind of model do we use? So since we know we are already dealing with a linear function, our model will also use a linear function in that case, which will be of that form. So we use our feature x times the weight plus the bias term, right? That is the definition of a linear function. But what we will do is to simplify our function a little bit, because that is more convenient to do the computations on, is to define an x train, because we are only using the feature x in our training. So x and y represents the whole data set already. And what we can do is we can include the bias into x, such that we don't need to add this term to our equation. So we're subsuming the bias term in x and call it x train, and then we just have to calculate it times the weight, and that's it. Basically, it's not an element-wise multiplication. We have to be careful here because we are dealing with arrays. So what is y hat? What kind of dimension does y hat has? And y hat has the dimension of instances, 1. In our case, we are not setting the 1 explicitly, so we have instances, comma, nothing. Then x. X has the dimension of instances, comma 2, and the weight. What kind of dimension does it have? Let us have a look. So we have 1001. This is y hat. This should be equal to x, and we know x as instances, comma 2. So when we compute the scalar product, we can use the numpy method dot for that. We know it has to be 2, comma 1, right? It will be an array with 2 entries. The 2 entries will be the weight and the bias term. Since we are subsuming the weight, the dimension will be 2, comma 1. So let us construct this xtrain and the weights. So for xtrain, what do we want? So we actually want to include a bunch of 1s, right? Because what is here? We have y hat is equal to x times the weight plus the bias times 1. And 1 is an array. So this is what we have to subsume, because the bias goes into the weight and the 1 goes into the x. So what we get is npc. So we use the numpy method c underscore. What this class does is it's stacking column-wise the arrays. So the first column from xtrain will be a bunch of 1s, and the second column will be x. So what are the weights? The weights will be just sampled from a Gaussian distribution. They are set randomly. In later episodes we will learn about more sophisticated methods of initializing the weights, but for this simple problem it will be sufficient. So let us print the shape. So let us execute our script, and we get for xtrain we have the shape 1000,2, and for weights it's of dimension 2, and this is correct. This is what we wanted. One note: when working with NumPy, the package NumPy, you have to be careful when doing computations. So be aware of the broadcasting rule. What are the broadcasting rules? Basically, the broadcasting rules are telling NumPy how NumPy should do computations in regard to the dimensions of the arrays. And for example, let us do 3 examples in order to understand the broadcasting rules a little bit more. So for the first example, we are constructing 2 arrays, one with a dimension of 101 and the other one with only 100 as a dimension. And when we do a minus b, what would you expect the result to have as a shape? Think about that for a second, but let's also construct 2 other examples in order to compare them with each other. So we have np_random.randm 100,1, b will be 100,1, and c will be again a minus b. And then let's print the shape of c again. And for the third example, we will use 100 and 100, a minus b, and then the third shape of c shape. So what would you expect? Well, in the second and third example should be pretty clear. Since the dimension is 100,1 and 100,1 in the second example, we expect C to have the same shape as A and B. In the third example, the same. It's only the first dimension is set with 100, 100, so we expect the shape of C to be 100 without the 1. But the first example is where the broadcasting rules of NumPy kicks in, and where we have to be very careful, because that can that can be confusing for beginners who didn't work with NumPy arrays a lot. When we try to compute, for example, try to subtract two arrays with different kind of shapes. For example, in this case, the shape is 100,1 and 100. These two are not the same in NumPy's view. So what NumPy will do is it will have a look at the last dimension of A and will see that there's a 1. So what it will try to do is actually match it with the first dimension of B. So what it will do, it will broadcast the C array to the dimension of 100, 100 instead of 100,1. And we can see that when we execute our script, we can see in the first case, we really get 100, 100. And only the second and third example would result in a shape that we would expect. And in the first case, we would not necessarily expect the result to have that shape. So just be aware of the broadcasting rules. Okay, let's continue with our model. Let's delete these rows, these lines, we don't need them. Okay, so what will we give as an input? So of course for the model we need x. We also need the weights. And we will pass NumPy arrays. And we can even check if the second dimension of x doesn't match the first dimension of the weights, then it should raise an error. Simply because the second dimension of x has to match the first dimension of the weights. The reason is because we are essentially, because in principle x is a matrix and weights is a vector, and we know from math that the second dimension of a matrix has to match the first dimension of a vector in order to be able to do a computation on them, to multiply them with each other. And then we can do x.weights. Okay, so far so good. Let's make a test. What is the model shape? If we simply plug in xtrain and the weights, and as we can see, the model shape is 1000, which is correct, because because our input is 1000 data points, so our model should also output 1000 predictions. Next, define an objective function and the gradients. We will use the gradients in order to update our weights with gradient descent, and we need the objective function to tell us how far we are away from the optimum solution. So we will use a very popular objective function which is the mean squared error. So for the mean squared error we need y hat. Why is that objective function very popular? Well, that is because it's a convex function, so when we apply gradient descent we can be sure that we get very close at least to the optimum solution. Okay, so, and here we can also say if y hat shape doesn't match the shape of y, then something must be wrong. And we can return 1 over instances, so that's the definition of the mean squared error. This is just a scaling value, and then we have y hat minus y times t. So we have to transpose this vector times dot y hat minus y. So if it is unclear why you have to transpose that, think about the value which should come out. So the mean squared error is a loss function, and a loss function should output a scalar value. So 1 over instance is already a scalar value, but y hat minus y, that two are arrays, and when we subtract them we get an array. And when we have an array, in order to make it a scalar value, we can do a scalar product. So in this case, we do a scalar product with itself, because the definition of the mean squared error is that we have that expression squared. In order to compute the square value of two arrays, we have to take the first one, the transpose of it, and then apply the scalar product. Now we need the gradients. For the gradients, what we will need is again y hat and y. And yeah, for the MSE we don't get an array back, but we will get a float. And what we will get from the MSE gradients, here in this case we really get a numpy array. So, and we can again check. Now we can simply copy and paste that. Then, what do we return? We return 2 over instances. Why the 2? Because we have here a squared value. So when we take the derivative, then we get a 2 in front of it. Because note, the MSE gradients is essentially our loss function differentiated with respect to the weights. So when we take the derivative of the main squared error with respect to our weights, we get from this squared value the 2. And then what do we get? We have to apply the chain rule, because y hat, remember, is x train times the weights. So if we differentiate with respect to the weights, we get x train, right? So what we get is x train, the transpose of that, then the dot product y hat minus y. So far so good. And we don't need to pass x train as an argument to our mean squared gradient, because it's already in the scope, and x train will not change. Only the weights will change during the training process. So let's continue with the model training. So what is the learning rate? We can pass a very conventional choice for the learning rate, for example 10 to the power of minus 4. And it's very important when you choose your hyperparameters that you try out different values. Especially here in that case, the training doesn't cost a lot, it's very fast, so we can play around a little bit with the hyperparameters. Try and play around a little bit with them, since you can learn a lot about them and how important it is to tune them. Because when you take the wrong learning rate, you will get very crazy results and not what you would expect. So, the number of epochs. How long do we want to train? So let's start with 100,000 epochs. This is kinda long, but the computations we have to do are not that heavy, so we can manage that in quite a fast time. Let us save the unoptimized weight so that we don't lose it, because we will update the weights in place. Then we have the history. So for the history, we want to record some values during the training. And for example, one thing which we want to store for each epoch is the weights. Because later on we will plot a few weights and see how our training evolved during our training. So the loss history. So we just use 2 empty lists in a dictionary. And let us print also the unoptimized weight. Just to compare with the weights after the training. And then we can start the training loop. What we iterate and use TQDM for the progress bar, but remember you don't need it. And then we range over the number of epochs. Now, the first step when we are training our model is to compute the model prediction. So y hat. And y hat is just the model where we have to pass x train and the weights. Then we can calculate the loss. The loss is given by the mean squared error. So y hat and y. And we also need the gradients in order to update our weights. The gradient is the MSE gradients y hat and y. That's all we have to pass, and then we can use gradient descent in order to update our weights with the learning rate and the gradients. Let's line those up. Okay, and of course we want to record our loss history, so we will append the loss, and we want to record the weight, so we append the weights, but beware that you have to copy the weights, otherwise the weights will get updated inside of a list, and that's not what we want. And then and let's print the optimized weights in order to see how these weights changed after the training. Okay, let's start training and just see if it works. And as we can see, we started out with the following unoptimized weights. We start out with a bias term, which was 0.67, and the weight, which is 0.878. And after optimization, our bias term is approximately 30, and our weight term is 0.5. Okay, so far so good. So what we can see is that the weights did in fact change due to our training, but we still have no feeling whether our training was successful or not, if our model was able to learn from the data or not. In order to see if our model learned something, we can do some plots. So we call that model performance monitoring. In that case, it's not a continuous monitoring since we are only training once. So we just do two static plots. So we need x. And we will go, so we define x as going from 0 to 100 with 1000 steps. And then we have to construct xpred. Why do we need those? We need those because we will use them in order to generate model prediction, which we can plot. So xpred will be the stack columns of NP1s. This is what we did before, and x. Okay, so far so good. Then we can, what we want to do, so in the first plot, what we want to show is our toy data, our untrained model prediction, and let's say every 10,000th step of training of the model prediction. So because we are doing 1000 iterations during our training, and so we want to sample from those 100,000 epochs 10 models which we get from our history in order to see how our model prediction evolved over the epochs. We don't want to plot 100,000 different kind of model prediction. We wouldn't understand the thing from the plot. So what we do is we take every 10,000 weights and compute the model prediction from that. So what we need to do is we take our history, our weights history, and take every 10,000 step the weights from the history. Then we can calculate the model prediction history. So we can say, okay, for weight in history, in weights history. Wait, this should be weights history. Okay, so far so good. And then model pred history, append. And we append the model prediction. And the model is basically xpred dot weight history, right? But we can also call model. A model takes x and the weights, and x is in our case xpred, and the weights would be weight history. So far so good. And then we can print the shape, just to check. And this is an advice which I always can recommend, is to check the shapes and the dimensions of the results and of what you are defining in order to double check if what you are coding up is correct. Or maybe sometimes it still won't be correct, but it's a good indication if you're moving into the right direction. So the model prediction shape. Let's execute that. And as we can see, we really get 10 model predictions for 1000 values, x values. Okay, great. So let's plot that. So we will use Plotly, and for Plotly we can create a figure instance with GoFigure, and then we can add traces. And what we want to add is, for example, a line plot, and a scatter plot. For the data, we will want to use a scatter plot. How do we do it? We call GoScatter, and then x, we pass x and y, and the mode is markers, and the name is toy data. Then we iterate over the model predictions, model pred history. That's why we computed it beforehand. And then we can add a trace, GoScatter, we pass x, we pass the model prediction, we take as a mode the lines because we want line plots, and the name is the epoch 10,000 times the index. So far so good. And then we can add a last trace, GoScatter, x times x, y, x, take the model, x pred, and the weights. So this time we take the optimized weights. We again want a line plot, and the name should be the trained model prediction. So in that way we get the untrained model predictions, the model predictions every 10,000 step, and the trained model prediction. So we can see the end result. How our model prediction looks like after 100,000 iterations of training. So let's update the layout. Let's give it a meaningful title, linear regression on toy data. X-axis title, which is x, y-axis title, which is y, and let's increase the font size to 20. And then we can call fig_show in order to visualize the plot. But before we will execute our script again and have a look at our plots, we will create another plot, which is kinda important, even more important than this one. Because the first plot we can easily create when we have a very easy model. In this case we have just one feature and a bias term which can be easily visualized in a 2D plot. But imagine you have 1,000 features or 100 features or 10 features, 20 features, then you won't be able to visualize that in a 2D plot. So at maximum you will be able to create a 3D plot. Everything else will be not comprehensible for our human brain, since we are not used to think beyond 3 dimensions. So what we can do in that case is to create a plot which will visualize the loss against the epochs. In that way we can also see if our training was successful or not. So we are adding a trace again, and this time we have for x NP array, range, number of epochs, yeah, because we want the epochs on the x-axis, and we want the history, loss history on the y-axis. The mode is lines, and the name is loss. And then we can just copy and paste the update layout in the fig show, and that's it. Simple as that. So let's execute the script, and I see you in a second when we talk over the plots. So let's talk about the plots which we generated. So this is the linear regression plot on our toy dataset. And this is how our toy data looks like. We have y on the y-axis and x on the x-axis. And as we can see, this is a very linear data with some noise to it. Let's have a look at the beginning with our untrained model prediction. And as we can see, our untrained model prediction is very wrong. But how did our model prediction evolve during our training? And as we can see, when we see our model prediction and at the 10,000th epoch, we can see it got a little bit better, right? Because the y-intersection went up. This is what we want, and the slope is now rather matching the slope of a data. So how does it look like for 20,000 steps? Better. For 30,000, also better, and so on and so on. As we can see, every 10,000 step we can see an improvement, and the improvements get smaller and smaller. Since imagine that the mean squared error is a convex function, right? So the gradient at the beginning on a random point will be greater than when we get closer to the optimal solution. Because when we get close to the optimal solution, the gradients get smaller, so our changes get also smaller. And this is also what we can see. And this is our trained model prediction. And as we can see, our trained model prediction lies very good inside of the toy data. So let's have a look at only our trained model prediction and at the beginning of the model training. And as we can see, we really trained a model that is able to fit to the toy data set. Great! We did it! We trained our first model that was able to fit this linear function to our toy data. In the next episodes, we will ramp up the training process and improve on our algorithms, such that we can effectively fit even more complex data. So let's have a look at our second plot. What we got is the loss history. So on the y-axis we got our loss, and on the x-axis we got the epochs. And since we started from 0 epochs and went to 100,000 epochs, and our loss started at a value of approximately 250. And as we can see, so the more iterations we went up, the more the loss decreased over the number of epochs. And as we can see, around 70k or 80k, the loss didn't change a lot. And at the beginning we made larger steps because the gradients were larger, so our updates had a greater impact on our model prediction. As we can see, the loss, especially at the beginning, went really fast down. And here we can really see that our model did learn something, because the loss continuously decreased. But, as you might guess, this is not the whole story, because this is only the loss for our training dataset. And maybe you've heard already that in reality, you often divide your dataset into a dev set, a validation set, and a test set. And these different datasets have different roles during our training. And these sets help us to really see if our model is correctly working, because we don't train a model just out of fun. We want to solve business problems with that. And when we do some predictions, for example in a regression task, we want to know if our model would perform as good as during the training when it sees data that it didn't see before. And for now, I want to say we shouldn't bother with that, because we are starting up with very basic stuff. We are building up our foundations, and I believe that is the right strategy to take when you want to learn how to do machine learning. To start from the foundations, build a strong foundation, and from there evolve to more complex tasks which are closer to reality. And in the next episodes, we will evolve our techniques and refine them and see how we can improve on them such that our training algorithm is able to fit more complex data, to fit more complex functions. Stay tuned, and I see you in the next episode. See you then.